Hello again. Welcome to our final recap video. Don't have a whole lot to do today because only Monday's class covered new material, which was applications of Taylor series, and really getting into why do we care about this stuff, right? Why is it important that sometimes I can represent a function as an infinite polynomial, right? That's what a Taylor series is. If you think about it, it's a polynomial with infinitely many terms. Why is that important? Well, there's a big downside there. The downside is it's an infinite polynomial, right? Infinity is of course always going to be a bit more complicated than finite things. So adding infinitely many terms together is just innately more difficult than finite polynomials. But the big upside is, even though it's an infinite polynomial, it's a polynomial. And polynomials are nice, they're friendly, they're easy to work with, easy to add together, easy to differentiate, easy to integrate, very easy to understand. So if you can represent a function by a power series by its Taylor series, then you have a big step up in the game already. You understand the function a lot better than you originally did, probably. So we'll do 3 applications today, and we'll get started. Alright, so our first application is going to be this limit question here. Evaluate the limit as x goes to 0 of this function 1 minus e to the minus x squared all over x. So first thing you always do with limits, right? Just try to plug in x equals 0. That's maybe it equals something nice and we'll be done. But of course we can see we're going to be discontinuous at x equals 0 because we're going to divide by 0. And the top is, let's see what happens. As x goes to 0, 1 minus e to the 0, so 1 minus 1 up top is 0, over 0, it's a 0 over 0 indeterminate type. So one thing you could do, and I believe this is really the only tool you have at this point, evaluating indeterminate limits, you use L'Hopital's, right? But the question is, let's do this without using L'Hopital's. And that might feel a little unnatural to you. You might say, why, if I already have a perfectly good tool? Yeah, you could very well do this problem with L'Hopital's. It wouldn't be hard at all. But mathematicians sort of liken that to using a cannon to kill a fly, is what they often say, right? Why invoke this huge, powerful theorem of L'Hopital's when if I just understand this function as a power series, which is just another way of writing the function, then I don't have to invoke all this powerful theory. So you'll see where this is going. Let's try to represent this expression as a power series, right? And the first thing I'll do is I'll just recall that I know a power series expansion for e to the x, right around 0. E to the x is the sum, n goes from 0 to infinity, of x to the n over n factorial. And that's true for all values of x. So I'm not even going to write down the fact that it's true for all x, but it is true for all x. What does that mean? Well, now if I want, say, e to the minus x squared, just substitute in minus x squared. So minus x squared to the n over n factorial. And I'm going to write this in a nicer form here. What do we have? Minus 1 to the n, I'm going to write outside, so it's clear it alternates, minus 1 to the n. And then x squared to the n, we often just write that as x to the 2n, right? Over n factorial. So now I have a power series expansion or expression for that part. If I want 1 minus that, well, I could just do 1 minus that, right? So let's see. So 1 minus e to the minus x squared, that's 1 minus this summation. Minus 1 to the n, x to the 2n, over n. And it turns out for this problem, I'm not going to need all infinitely many terms, so how about I just start expand this out. Let's write out the first few terms. It'll become clear what happens, I think. So if I write out the first few terms, we've got 1 minus, now what happens? N equals 0. Oops, that would have been a problem. I would have been dividing by 0. I forgot my factorial there. Right, n factorial on the bottom. N equals 0. I've got positive 1, x to the 0 over 1. So it's 1 minus 1 is our first term. And now we're looking at n equals 1, so we're doing minus x squared over 1. And then this just causes it to alternate every time, so now plus n equals 2, x to the 4th over 2 factorial. Now minus n equals 3, x to the 6th, minus x to the 6th over 3 factorial, which I write as 6, plus dot dot dot. Right, I'm running out of space. Okay, so what is that? Well, let's actually just subtract these terms from 1. 1 minus 1, those guys cancel. And I'm just left with minus x squared plus x to the 4th over 2 minus x to the 6th over 6 plus some higher power, some higher order terms of x. Okay, so there's a power series expression for the numerator. 1 minus e to the minus x squared. The last thing I'm going to do is just divide by x. So I'll save this. This means 1 minus e to the minus x squared over x is all this stuff divided by x. So divide each term by x. What am I left with? Minus x squared over x? That's minus x, right? Plus x to the 4th over 2 divided by x, that's x cubed over 2. Minus x to the 6th over 6 divided by x, that's x to the 5th over 6. And plus, what do I have? I have higher order terms. So there's the first 3 terms in the power series expansion of this function, right? And this is literally equal to this function, so I should be able to evaluate the limit as x goes to 0 of this function, I can take the limit as x goes to 0 of this function. Well, this is a really easy function to see what happens, right? As x goes to 0, what's happening to this expression? X goes to 0, x cubed goes to 0, x to the 5th goes to 0, all these higher power terms of x go to 0. So clearly, the limit as x goes to 0, 1 minus e to the minus x squared over 2, that equals 0, right? Just by taking the limit of, well, I shouldn't have cut this off, the limit of all this stuff instead. So this is the gist behind all of these applications. The gist is that understanding polynomials are very easy to understand. They're easy to work with. So if you think of a power series as just being an infinite polynomial, well, the infinity makes things a little bit harder, but the fact that I can understand even a complicated function like this is just a polynomial, that's a good thing. Because polynomials are really easy to understand and really easy to work with. In this case, taking the limit as x goes to 0 of this polynomial is not a problem at all. So the answer is that this limit equals 0. Alright, so here's our second application, and this is a fun one. Here's a function, just cosine of 3x plus e to the x squared, not a particularly scary function. And the question is, find, oops, bracket's way too big here, find the 40th derivative of f at 0. Now it's not a scary function, you could differentiate it once, you could differentiate it twice, but you'll soon find that differentiating this several times over becomes pretty painful, and theoretically you could brute force it, but you don't really want to differentiate this 40 times. There must be an easier way. And the answer is, use Taylor series. Right? In what sense do I mean that? Well, remember our coefficients in Taylor series, right? The general Taylor series is 0. The coefficient of x to the n is the nth derivative of f at 0 over n factorial. So if I can find a Taylor series expansion for this, I should be able to say something about the derivatives of f based on the coefficients in front of powers of x. So there's my goal. And to find the Taylor series expansion, we're just going to use known series. So I know cosine of x. Cosine of x, I know, because this is one of these ones you just memorize by heart. This is minus 1 to the n, x to the 2n, over 2n factorial. All right, it's the even powers of x, sine is the odd powers. And that means if I want cosine of 3x, I just have to plug in 3 everywhere I see x. All right, so this is n equals 0 to infinity, minus 1 to the n, 3x to the 2n over 2n factorial. I'm not writing down the intervals of convergence here or anything because it converges for all values of x. And one last thing I'll do is just clean this up a little bit more. This is minus 1 to the n, 3 to the 2n, 3 squared to the n, so 9 to the n. Right, 3 to the 2n is 3 squared, so that's 9 to the power of n, times x to the 2n. And can I fit it? I think so. There we go. Over 2n factorial. And yeah, there's a power series expression or expansion for a Taylor series expansion if you want, around 0 for cosine of 3x. Now do the same thing for e to the x squared. So e to the x, I know what that is. That's n equals 0 to infinity of x to the n over n factorial. Converges for all values of x. And if I want e to the x squared, let's just substitute in x squared for x. So this would be e to the x squared is x squared to the n over n factorial, or the sum of x to the 2n over n factorial. Awesome. Again, converges for all values of x. So now I have Taylor series expansions for this guy and this guy around 0. I want to find a Taylor series expansion for the whole thing just by adding them together. So cosine of 3x plus e to the x squared, that's the first summation, minus 1 to the n times 9 to the n times x to the 2n over 2n factorial plus the second summation x to the 2n over n factorial. Well, that's not a power series as it's written, right? A power series should be a single summation, coefficient times x to a power, right? X to the n. So what I need to do is I need to combine these, right? I can't have two different sums, and I can combine them. Sometimes you have to do a bit of work. If the indexing here doesn't agree, if they start at different points, you've got to count off some terms. If the powers of x don't agree, you'd have to factor out an x or something to make them agree so that you can combine them together by factoring. But here my powers of x match up, they start at the same point, so I can just write this as a single power series, a single summation, n equals 0 to infinity of, I'm going to have some stuff, times x to the 2n, right? X to the 2n is common to both, so I'm going to factor that out. And what do I have from the first one? I've got minus 1 to the n, 9 to the n, over 2n factorial, plus from the second one, I've got just plus 1 over n factorial, times x to the 2n. Awesome. There's the Taylor series centered at 0 for f of x. So what now? How am I going to use this? Well, recall just the general form of a Taylor series of a function is the nth derivative of f. The Taylor series is 0. Nth derivative of f at 0 over n factorial times x to the n. Right? So these coefficients here match up with these coefficients here. That is, that the coefficient of the 40th power of x, the coefficient of the 40th power of x should be the 40th derivative of f at 0 over 40 factorial. So what is the coefficient of x to the 40 over there? Well, when does x to the 40 happen? X to the 40 would happen when 2n is equal to 40. Right, so we want 2n to equal 40. Well, that means n is 20. All right, so if you're counting those out, the 20th term corresponds to x to the 40, and the coefficient of x to the 40 happens when n is 20, is going to be the 40th derivative of f at the 40th derivative of f at 0 over 40 factorial. So let's just figure out what this is. If n is 20, what's my coefficient? Coefficient is, n equals 20 coefficient is, what do I have? Minus 1 to the 20 times 9 to the 20 over 2 times 20, 40 factorial, plus 1 over 20 factorial. Alright, or just cleaning this up a little bit, that's minus 1 to the 20 is just 1, right? So 9 to the 20 over 40 factorial plus 1 over 20 factorial. Great. So there's my coefficient. If I was writing out this power series, when I get to the x to the 40 term, my coefficient is this. Right? But my coefficient of x to the 40, has to be 40th derivative of f at 0 over 40 factorial. And for any Taylor series, the coefficient in front of x to the 40, any Taylor series ending at 0, is the 40th derivative of f at 0 over 40 factorial. Well, for this function, this is the coefficient of x to the 40. So they must be equal. Right? The coefficient of x to the 40, 40th derivative of f at 0 over 40 factorial, must equal 9 to the 20 over 40 factorial plus 1 over 20 factorial. Plus 1 over 20 factorial. So I want the 40th derivative of f at 0, I just have to solve for it now, right? So 40th derivative of f at 0, multiply both sides by 40 factorial, I've got 9 to the 20 plus 40 factorial over 20 factorial. And there's not a whole lot I can do with that second term there. I'm just going to leave it that for 40 factorial over 20 factorial. So there's my answer. I promise you, if you were still differentiating this, if you were trying to brute force this, trying to differentiate 40 times and plug in 0, you'd still be going, right? But we're already done. So the idea here, the idea to find these very high order derivatives is find a Taylor series expansion instead. If you want the 40th derivative, look for the coefficient of the 40th power of x. If I wanted the 88th derivative, I would look for the coefficient in front of the 88th power of x, right? Because this tells me, in general, my coefficients have something to do with the derivatives. The derivatives divided by n factorial. So here's one of my favorite applications. Integrate sine of x over x dx. And this is hard, right? No techniques we've learned so far in this class will allow you to integrate this. And I don't believe an antiderivative exists, right? I don't think in terms of elementary functions one exists at least, right? That's what I mean when I say one doesn't exist. It doesn't mean that there's nothing out there that differentiates to give me this function. It's just we don't have a name for that. It's not an elementary function we're used to working with, but I can do this in terms of power series, right? So integral of sine of x over x dx, well that equals power series for sine of x. This is one we have sort of memorized, right, by heart. That's just going to be minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And then divided by x, well that means multiply by 1 over x is the way I'm going to interpret that, right? Okay, still not in a form that I can work with, but all I have to do here to deal with this 1 over x term is bring it inside. So this would be the sum of minus 1 to the n, x to the, if I divide by x, I'm subtracting 1 from my power of x on the inside, right? Because this is x to the minus 1 if you want. So this is just x to 2n over 2n plus 1 factorial. And now I want to integrate this. And the nice thing about power series is you can integrate term by term, right? So if I integrate this, I think I can fit it down here. If I integrate this, what do I have? X to the 2n, that integrates to x to the 2n plus 1, right? Increase the power by 1. And then divide by the new power. So 2n plus 1 times 2n plus 1 factorial. And unfortunately, there's really nothing I can do with that. I have to leave it in that form. Oops, I've already integrated. Okay, so I integrate that expression plus c, plus some constant. So if I write out the first few terms of this, what would this look like? If I just were to write out the first few terms, n equals 0, I've got x over 1 times 1, so I've just got x. Then my minus 1 to the n makes me alternate, so n equals 1 minus x cubed over 3 times 3 factorial. Plus x to the 5th over 5, right, n equals 2, 5 times 5 factorial, minus x to the 7 over 7 times 7 factorial. But there's the antiderivative for this function sine of x over x. Meaning I can integrate it, I can find an antiderivative, I just don't have a name for this function, right? This is not equal to some elementary function we're used to working with, so I don't have this nice, beautiful solution, but I can integrate it. I just have to integrate it in terms of power series. And here's my answer in terms of a power series. Okay, so where was I going with this? Well, so okay, so I can integrate these kind of scary functions now. Let's do an approximation instead. So let's modify this question. Let's approximate the integral from, say, 0 to 1 of sine of x over x dx using the third order Taylor polynomial. P sub 3 of x for sine of x over x. Okay, so I think we just agreed that sine of x over x, right, we wrote out a Taylor series for this. This was minus 1 to the n, x to the 2n over 2n plus 1 factorial. So this equals, let's count out, I want to go up to the power of x cubed, right? I want the third power of x. That is the third order Taylor polynomial. So if n is 0, I have just 1 times 1 over 1 factorial, so just 1, right? n is 1, I've got minus x squared over 3 factorial. Oops, sorry, that should have been minus. And then plus, if n is 2, I've got plus x to the 4th over 5 factorial, and so on. I want the third order Taylor polynomial. That means I'm going to truncate it after x cubed. Well, it turns out the coefficient of x cubed here is 0, so this is just my third order Taylor polynomial. Right, I'm technically including x to the cubed, or x to the power of 3, but it's plus 0 times x to the 3. So it is in there, it's just times by 0. So yeah, so this integral, sine of x over x dx, is approximately the same as this function is approximately the same as any one of these Taylor polynomials, right? You count out further, you get a better and better approximation. Here we're just using the third order Taylor polynomial, so it's approximately the same as the integral of 1 minus x squared over 3 times 2 times 1 is 6 dx. And from here, this is a very easy integral, right? This integrates to x minus x cubed over 6 times 3 is 18 from 0 to 1. So plug in 1, I've got 1 minus 1/18, which is 17/18. I haven't used a calculator. I haven't used a calculator to figure out exactly what the value of this is to any order of precision, but it should be very, very close to 17/18. So this should be a pretty good approximation right off the bat. So that does it. We've done 3 applications. We did a L'Hopital's type question where we realized you don't really need these high-powered results of L'Hopital's to evaluate limits if you understand your function as a power series, because polynomials are really nice. We did an application where we used our power series to find very high-order derivatives of a function at a particular value at 0, or the point you're centered at. And we did this one. I really like this one where you approximate these difficult integrals, right? These integrals that don't have elementary antiderivatives, and up to this point, our only method for approximating these would have been numerically using Simpson's rule or what was it called? The trapezoid rule, or just doing Riemann sums if you want. So we could approximate the area of the curve geometrically, but now if we just represent our function as an infinite polynomial, once again, polynomials are really nice, really easy to integrate. So this provides another really nice approximation technique for these hard integrals where antiderivatives, at least in elementary terms, don't exist. Okay, so that's it. We've covered everything that's covered in Calc 2. We're done. I will say one thing: if you go into Calc 3, you won't do much with these power series, these Taylor series in Calculus 3. But if you take a class in differential equations, just like standard ordinary diff-EQ, you will start to see the power behind this. You'll use these all the time to solve differential equations. So you'll maybe come back and appreciate just how useful this stuff really is. But today we've tried to lay out a few applications of this stuff, and even this application right here, just approximating these tough integrals, I think are really useful. Anyway, I hope you guys have found this recap series to be useful. If you have any questions, please let me know. Otherwise, I wish you guys well on your final exam and in the future with everything. Thank you.